So yesterday we were discussing this topic, right? Diffraction of light. So in that, what did we see? By the way, people who are online are able to hear me?
Yes, sir.
Those who are online, am I audible?
Yes, sir.
Okay. So what were the concepts we were discussing? It is phenomenon of diffraction, that is bending of light when it strikes a sharp obstacle. So when light is traveling in a path and there is some obstacle that is there, once it starts bending, you call that phenomenon diffraction. If that bending happens within an opening whose size is very small, so if the size is comparable to the wavelength of light that is being used, then what will happen? You will be able to observe an interference pattern on the screen, right? But here what is happening? You have only one slit. Hence, diffraction experiment can also be called as a single slit interference. Right? This is what I told you. So you can also call it as a single slit interference. Generally, for interference, you need two openings, but here you have only one opening. So that one opening is assumed to be broken into multiple openings for us to give explanation of why there is a bright fringe or a dark fringe at a particular location. Is that right? Now, if you see, for central bright spot, what was the explanation that we gave? That the ray coming from the top and the bottom, they both are traveling the same distance, so that the path difference between them is zero. As a result of which, you have the central spot to be the brightest spot, which you also call it as central maximum. So after central maximum, what do you have? You have subsequent minimum, maximum, minimum, maximum. So after the central maximum, we need to give an explanation for the first minimum, right? So for first minima, what is the explanation we took into consideration? Though there was a single slit, we broke it into two slits, and in those two parts, between the two parts that were assumed, we took two rays which are symmetric with respect to each other. And those rays went and fell on the screen in such a way, they underwent destructive interference, right? If that should happen, then if I take the distance between those two successive rays to be a by 2, right? We chose in such a way that the distance between them is a by 2. Then we drew a separate triangle to understand what is going to be the path difference. What came out to be the value of path difference? It came out to be a by 2 sine theta. And a by 2 sine theta should be equal to what value for it to have a destructive interference? A by 2 sine theta should be equal to lambda by 2. So 2 and 2 will get cancelled. You will have a sine theta is equal to lambda. And the condition for the first minima is a sine theta is equal to lambda. Is that clear? Similarly, for the first secondary maximum, what the explanation? We broke the bigger slit into three equal parts. We considered three symmetric rays. Of those three symmetric rays, what will happen? The first two will go and fall on the screen to undergo destructive interference, and the third one will go and fall on the screen to fill the gap, so that you have slight brightness, which is going to produce some intensity on the screen. Is that right? And what is the condition for it? For these two rays, the first two rays to undergo destructive interference, the path difference between them should be equal to lambda by 2. Why lambda by 2? Because they are also successive rays. So a by 3 sine theta 2 should be equal to lambda by 2, or a sine theta 2 should be equal to 3 lambda by 2. Right? Similarly, for the second minimum, what will you say? You break it into 4 parts, and a sine theta came out to be 2 lambda. And for secondary maximum, what happened? You broke it into 5 parts, and a by 5 sine theta came out to be lambda by 2, and a sine theta is equal to 5 times lambda by 2. So like this, if you keep proceeding, then you will have a generalized expression. So for the first secondary maxima, you have a sine theta is equal to 3 lambda by 2. Secondary maxima, you have 5 lambda by 2. And for the nth secondary maxima, you have 2n plus 1 into lambda by 2. And for the first minima, what is the condition? A sine theta will be lambda. Second minima, a sine theta is 2 lambda. So like this, if you keep on going for the nth minima, you have A sin theta is equal to n times lambda, right? So based on these concepts, right? Based on these concepts, we are going to see the relation between the width of central maxima and any other maxima. Okay, so the heading is width of central maxima and any other maximum. So if you observe this, if I take this to be a dark spot and this to be a dark spot, then this whole is supposed to be a bright spot. Because where will a bright spot lie? So if I take this to be the bright spot, the top of the bright spot will be dark and below that it will be dark. So this whole region is going to be a bright spot. For which, what I'm going to do is, if I take this distance to be capital D, for instance, okay, this is dark and this is also dark. Listen to this carefully. If I take this distance to be capital D, and if I take this angle to be theta, is that clear? So if I take this to be beta, then remember all the angles that we are considering this experimental setup are very, very small because the opening of the slit itself is fixed. Right. So when that is going to be the scenario, and one more point to be kept in your mind is all the angles that you're taking are measured in terms of radians. Okay, no angle is measured in terms of degree. So when you measure something in radian, from trigonometry, what does radian tell you? What is the definition of radian tell you? Theta is defined as arc length divided by radius, accepted? Right. So what is going to be the arc length here? Is it not beta? Right. So theta is equal to, can I say arc length is beta? Are you guys able to visualize? Because this arc is so small, because the angle itself is so small that the arc is appearing like a straight line. Right. So beta divided by what is going to be the radius of this? It is going to be capital D. So everything is an approximated value here, which implies beta is equal to capital D into theta, accepted? Right. But are you able to understand? Can I proceed? Now listen. If I draw a line like this, if I draw a line exactly breaking this angle into two equal parts. So if I take this to be alpha and this to be alpha, right? So with respect to the horizontal, I'm saying, the ray is getting bent at an angle alpha, so that the ray which is getting bent at an angle alpha is creating a dark spot here. Accepted? So which dark spot is this? Since we are calculating the width of the central maxima, above and below the central maxima, you will have the first dark spot. Accepted? So what is the condition for first minimum? It says A sin theta is equal to lambda. Right? But in this case, what will happen to theta is basically the angle made by the ray with the horizontal. So I will replace theta with alpha. So I can say A sin alpha is equal to lambda, but remember the value of alpha is going to be so small that sin alpha can be approximated to alpha itself. So I can write A into alpha is equal to lambda, which implies alpha is equal to lambda divided by A. Right? So alpha is equal to lambda divided by A, and we wrote beta is equal to d into theta, right? Listen to this. So d into, can I write this theta as 2 times alpha? So I write it as 2 alpha, or d into 2 into, what is the value of alpha here? It is lambda by A. So beta will be equal to 2 into lambda into capital D divided by A. Let me call this as 2. So this is the expression we are going to remember. So the value of beta in terms of wavelength, the distance from the opening to the screen, and the width of the slit is given as 2 times lambda into capital D divided by A. I didn't take this A sin theta is in the derivation. That theta is what? That theta is the angle made by the ray with the horizontal. In this case, I took this whole angle to be theta, so don't get confused between this theta and this theta. If it is confusing you, I'll write it as theta 1 here. A sin theta 1 is lambda. Trying to understand one point here. Here also we did one thing that we had been doing from the beginning. What is it? To calculate the width of the brightest spot, we took the condition for the darkest spot. That's what we have been doing throughout the derivation. Right? Whether you have a first minima or first secondary minima, second secondary minima, whatever it is, we are trying to say if there is a dark spot at that particular point formed due to a set of even number of rays, then the fifth ray or the sixth ray, then the odd number of ray will go and fall on the screen to give you some brightness. In a similar way, if you want to calculate the width of any maximum, you need to actually calculate the width or the difference between the subsequent dark spots that are available. So to put it in simple terms, the width of this bright spot, which I calculated here, is also the distance between the first dark spot at the top and the first dark spot at the bottom, which is symmetric with respect to the center. They both mean the same. So using the same logic, what I'm going to do is to calculate the width of any other maxima, I need to calculate the difference or the distance between two subsequent dark spots. Logically, right? Right? So what am I supposed to do? If I take this to be the nth dark spot, and this is the n plus 1th dark spot, right? From the center, I have a ray which is bending, let's say, at an angle theta n here, and here it is bending at an angle theta n plus 1. Okay, so the distance that is there between the n plus 1th dark spot and the nth dark spot is going to give us the width of the maxima that is available. Is it right? So, what is the condition for the nth dark spot to be formed? So, A times I can write sin theta n is equal to n lambda. And what is the condition for the n plus 1th dark spot to be formed? A sin theta n plus 1 will be equal to n plus 1 times lambda. Right? But what did we say? That these angles are going to be so small that the value of sin theta can be approximated to the angle itself. So when I do the approximation, I will get theta n is equal to n lambda divided by A, and theta n plus 1 I will get it as n plus 1 into lambda divided by A. So if I calculate the distance between them, right? So how much is it going to be? Again, the distance here is capital D. So what can I take them to be? So if I calculate the width of this spot, if I call this as beta, previously what they call, they called it as beta, I'll call it as beta 1 for instance. Okay. Then beta 1 will be equal to this angle, except this angle times the radius. Right, because the whole setup is going to be so small that this distance can be approximated to the radius itself. So I can write this as capital D multiplied with theta n plus 1 minus theta n, accepted. Theta n plus 1 minus theta n is going to be this value. Right. So theta 1 will be equal to capital D into what is the value of theta n plus 1 minus theta n? It is going to give us lambda divided by a. Why? Theta n plus 1 is n plus 1. Theta n is n. So n plus 1 minus n will give us 1. So 1 multiplied with lambda by a. That's what I will get. So beta 1 will be equal to d into lambda by a, or lambda into capital D divided by a. If I take this as 2, if you observe the relation between beta and beta 1, beta will be equal to 2 times beta 1. Means the width of the central maximum in the case of diffraction is always twice the width of any other maximum that you can see. This is a very, very important expression. So you can either tell it in terms of width, or you can also say in terms of angular width. Both are angular width means only in terms of angle. Okay. So this is a very, very important relation that is used in many problems. Is it clear? So sometimes what they will do is they'll give you the width of any maximum, right? And they'll ask you to calculate the width of the central. Just need to multiply it with 2. Or they can do the vice versa. They'll give you the width of the central maximum, ask you the width of any other maximum divided by 2. Okay. Shall I proceed? Shall I proceed? So the last concept in this chapter is we are going to see the graph for intensity as a variation of distance from the screen. So if I take this to be the screen, you have central maximum here, first secondary, second secondary, third secondary, it keeps on going like the same is the case, symmetric exactly at the bottom also, right? If I just tilt it, okay, and draw it horizontally, see what is going to happen. If I take the distance on the x-axis and intensity on the y-axis. Okay. So at the central part, the intensity is going to be maximum. Right. So what is happening? At the central spot, the intensity is maximum. Surrounding it, the intensity will decrease. So that this is the first dark spot on the left, and this is the first dark spot on the right. Actually, if you have to visualize, this dark spot is this one, and this dark spot is the top one. So since I rotated it, it is looking like this. Are you able to understand? So how far is the first dark spot formed in terms of angular distance? It is lambda by a and here it is minus lambda by A. Why is it so? Because we know the condition A sin theta is equal to n lambda. For the first minimum, you have lambda, which implies theta will be equal to lambda by A. So this is lambda by A, this is minus lambda by A. Where will the second dark spot be? So if you get 2 lambda by A, and here it will be a minus 2 lambda by A. So where is the first secondary maxima form? It is exactly, it is at the midpoint of these two. So that is 3 by 2 times lambda by A. So what will happen is, again the intensity will increase, but no, intensity is not half. Don't get confused. Intensity is, I never told intensity is half, only the width is half. Okay, keep going like this and comes down. Makes sense? So here you have 3 lambda by A and minus 3 lambda by A. Right? Again, it will go up and come down. Go up and come down. So like this, the graph will keep going in such a way that the intensity as we move away from the central spot keeps decreasing. Means this value keeps dropping like this. This is what happens with respect to light action. Means if you keep drawing it, it keeps going like this. Am I clear with this? Are you guys able to understand what I'm trying to say? So make a note of this, and this is the end of this chapter. Will you proceed? Did you all make a note of that? It started. The problem with respect to this chapter I have a final question. Tell me on the conceptually you guys are clear, right? Conceptually you are clear. As we discussed, it started with the next chapter. Shall we? You have any doubt? You clear? Everyone is clear? Those are online, are you clear?
Yes, sir.
Okay. So take a fresh page and start. Chapter 11, that is dual nature of radiation and matter. Right. So if you observe, in the previous 2 chapters, we were discussing mainly about light, because both the chapters are related to optics, right? So what is basically light? So light is basically electromagnetic radiation, right? So if you look at the name of this chapter, it says dual nature. Dual means nature of something. What is it? Something of radiation and matter. So when I talk about radiation, radiation that comes to my mind is something which carries energy, right? So something which carries energy, that is light. So what they're trying to say is light has dual nature. But the question is, who's producing that light? It is a particle which is in oscillation. That's what electromagnetic waves told us. So if you recollect, what is the source of an electromagnetic wave? What is it? It is an oscillating or a vibrating charged particle. So charged particles are what? They are matters because they have mass associated with it. Am I right? So when you talk about dual nature, it is not only restricted to the concept of the radiation, it is also extended to the concept of matter because science follows symmetry. That is what we are going to see in this chapter. If you again revisit the history of the previous two chapters, what did we see in wave optics? So in wave optics, we understood the fact that light had wave nature, right? So due to that wave nature, what were the phenomena that we could explain? What were the phenomena that we could explain? We explained the concept of interference, diffraction, and there is something else called as polarization. Right? These are the three important phenomena. But what happened is people started believing that light had only wave nature. You remember the corpuscular theory? So there we told that first Newton proposed that light had only particle nature. Then came the contradiction of wave theory. So wave theory started making people believe that it had only wave nature. Later what happened? There was an other activity that came into existence to say that light had both wave nature and particle nature because there are certain phenomena like interference, diffraction, and polarization which can be explained using only wave theory. And there is another important phenomena that we know it today, which is called as photoelectric effect, which can be explained using the concept of only particle nature of light. So from there, an important conclusion that was drawn is light is not restricted to having a single nature, rather it has both the natures, which will vary according to the context in which you're trying to give an explanation. Is that clear? And in this chapter, since we have already discussed the wave nature of light in the previous chapter itself, in this chapter, we'll be mainly concentrating on the phenomena which brought in the concept of dual nature. So the whole chapter, we're going to discuss only about photoelectric effect. But before we understand photoelectric effect, there are some basics which we need to understand with respect to the atomic structure and other parts. So I'll be starting from those points, right? So the first point that we need to understand is when you talk about a metal, right? So whenever you want this effect like photoelectric effect, photo comes from the word photons. Photons are basically light. Electric comes from the word charges. So with the help of light, if you are able to charge a material, then you can call that kind of a phenomena as photoelectric effect. Am I right? But the question is, if you need to charge a material, what does electrostatics tell us? The basics of electrostatics tells us the fact that for any material to be charged, there needs to be an imbalance that is occurring between the number of electrons and protons present in the system. Right? So if you want a material to get positively charged, what will you do? You will remove an electron. If you want the material to get negatively charged, you will add an electron. So the question of removing or adding an electron, if you take from the periodic table, is easy for what kind of materials? It is for metals. That is why if you see the photoelectric concept is restricted only to metals. We never discuss it for non-metals. That's an obvious reason, right? The question is, what do we call these free electrons in metals as? What are these free electrons in metals actually called as? So look at the name. Free electrons. If they are valence electrons, they are not free. Valence electrons are bound within the nucleus. Sorry, bound within the atom. They are not free electrons. Then what do these free electrons mean? When will something get free? When it is leaving that particular Coulombic force of attraction, right? So this is where we start. Now, what you told is partially right. Okay, listen. So when you talk about these free electrons in metals, when you talk about metals, the valence electrons that are there are loosely bound. And the reason why you call them as free electrons is because if you go back to the concept of current electricity, we used a name called as charge carriers. Do you remember what they are? What are charge carriers? Name is suggesting charge carriers. So the ones which participate in the conduction of electricity, right? The conduction of charges is what we call it as charge carriers. Inside metals, who are the main charge carriers? Electrons. And when you say electrons, you should use the word free electrons. And where do you get those free electrons from? From the valence shell. And there, what did we do? When we discussed the concept of drift velocity, I hope you all remember this. When we discussed the concept of drift velocity, I used a word called as thermal agitation. Due to thermal agitation, what happens? Even at room temperature, there will be some electrons which are free from the metal surface and they start moving inside. But how will they move? They move in a random fashion. But to make it move in a aligned fashion, what are we supposed to do? We need to apply some potential difference. That is a different story. But the concept of free electron or free electron comes from that context itself. So here, in metals, if you see, the electrons in the outer shells of the atoms are loosely bound. And how are they going to be? They move about freely throughout the lattice of positive ions. So if I take, so from your solid state chemistry, you would have understood what is a lattice. You have different kinds of structures, BCC, FCC, all those things. You have a lattice. Inside that lattice, what you will have is these electrons can move. So they move about freely throughout the lattice of positive ions. And such loosely bound electrons, which can actually participate in the conduction process, are what are called as free electrons. Are you able to understand? So this is the first term that we need to have in our mind. For this chapter, we'll be repeatedly using these terminologies. See, if you see, you already know this context. Okay? What I'm trying to do is I'm only trying to build the grammar of what is needed for you to understand this chapter. Is it clear? So listen to this. So the free electrons, however, what are they going to do? They are going to remain confined to the conductor and cannot leave its surface. Why? Because there is some electrostatic attraction taking place. And this cannot happen at ordinary temperature and under moderate electric fields. Means what the hint that they're trying to give us is if you need to remove an electron from the valence shell, you need to supply energy. So when you're trying to supply energy, that energy can either be in the form of heat or it can be in the form of electric fields or it can be in the form of field as well. So that is why when we discussed it in current electricity, we called it as thermal agitation because thermal energy made the electron come out. In this chapter, we'll make use of the fields. Okay. So this point you already know. The moment an electron comes out of a metal surface with its negative charge, the metal surface acquires an equal positive charge. But what will it try to do? It will try to pull it back. So you need to give it some sufficient amount of energy so that the electron which has escaped the metal surface is not going to go and sit on the valence shell again. Right? So that energy is called as the minimum energy. Can I say that is the minimum energy? That is the minimum energy that is required for you to take an electron out from the metal surface and pull it out of the electrostatic attraction from the nucleus. Am I right? Are you able to visualize what it is? And right. I'll come to that point. So write down what are these free electrons in metals are. First, in metals, the electrons in the outer shells of the atom are loosely bound. They move about freely throughout the lattice of positive ions, and such loosely bound electrons are called as free electrons. Am I clear with this point? right? Now listen. So I use the word called as minimum amount of energy that is required for whom? For the electron that has escaped out of the metal surface from not coming back into the atom. And what do you call that minimum energy as? If you have to give a name to it, what is it called as? It's called as work function of a metal. So this is another term. Okay. So what does this work function mean is the minimum amount of energy that is required by an electron to just escape from the metal surface. Okay. This is another word which we keep using repeatedly. So here a point to be noted is underline this word minimum. It is not maximum, it is the minimum energy that is required. Only if a value equal to this or slightly greater than this is given, it will come out. Okay. Next is, when you talk about the work function of a metal, it depends on the first thing, the nature of the metal. Okay. So you can ask me what are the factors on which work function depends on. First thing is it depends on the nature of the metal, and the second thing is it depends on the condition of its surface. Okay. And the symbol that is used for work function is W naught, or some books refer to it as phi naught. Right? It is written as W naught or phi naught. And since work function speaks about the energy, it should have the unit of energy. But when it comes to atomic physics, the energy is mostly measured in terms of electron volt. It is not measured in terms of joule. So the unit of work function is in terms of electron volt. So this is also another important term. Have it in your mind. So the unit of energy is in terms of electron. Right. Now the question is, what exactly this 1 electron volt is all about? Listen to this first. Suppose I have two metal plates. Suppose I have two metal plates which are charged. Okay, it can be either positively charged or negatively charged, or both being positively charged. It can be anything. Okay, so if I have two metal plates which are charged and have a potential difference of exactly 1 volt. How much? Exactly 1 volt, and you just take one electron. Right? You take that one electron and you make that one electron get accelerated between the potential difference of 1 volt. Means you have done a work which is equal to 1 electron volt. The reason is it comes from the concept of electrostatic potential energy. You remember this, U is equal to Q into V, where Q is going to be the charge of the material multiplied with the potential difference across which you are making the charge move. So U is equal to E into V, and this U is what is going to be called as the value of 1 electron volt in this scenario. Is it clear? Right? So now you can make a definition. So 1 electron volt is the amount of kinetic energy that we need, or kinetic energy that is gained by the electron when it is accelerated through a potential difference of 1 volt. Am I clear? So when it is accelerated through a potential difference of 1 volt. Listen. So 1 electron volt will be equal to 1 into 1 electron's charge is how much? 1.602 into 10 power minus 19 coulomb multiplied with 1 volt. Am I right? So this will be equal to 1.602 into 10 power minus 19 coulomb into volt. This coulomb into volt is called as joule. So 1 electron volt's value is equal to 1.602 into 10 power minus 19 joule. is equal to 1.602 into 10 power minus 19 joule. Electricity. This is what we have to do. So energy gained by an electron is equal to work done by the electric field. But work done by the electric field is Q into V, right? So 1 electron volt will be equal to 1 electron charge as 1.602 into 10 power minus 19 coulomb multiplied with 1 volt. So this is going to be the value. And generally, electron volt, as I mentioned, it is a commonly used unit of energy in atomic and nuclear physics. So in the next 3 chapters, we'll be using only electron volt. We will not use joule at all. So if anywhere you find joule, you will always have to convert it to electron. Is that clear? So I hope work function has got registered in your mind. Right. Now the next concept is about electron emission. Right. So what does electron emission mean? The name itself is suggesting. It is a phenomenon of emission of electrons from a metal surface. It's like a compound noun, right? So the phenomenon of emission of electrons from a metal surface is called electron emission. But for electron emission to happen, it is not a spontaneous process. For it to happen, what are all the things that need to happen? We have already discussed. We need to supply some energy. So for electron emission from the metal surface, the energy of electron must be higher than that of the work function.
Sir,
Yeah.
sir, is electron emission is same as photoelectric emission?
Photoelectric emission or electron emission. That is one of the types of electron emissions. That is what I am trying to build. I'll tell you the different kinds of electron emissions that are there. Then you will understand about the photoelectric emission.
Okay.
Okay. So let me know once you're done. Right. Can we proceed? Listen. So I hope this point has got registered. For the emission of electrons from the metal surface, the energy of electrons must be higher than the work function of the metal. Only then they can escape. Right. So, since we are discussing about the different kinds of emission that are possible, we need to think of what are all the possible ways in which we can supply energy. Right. So, for the release of electrons from the metal surface, they may be supplied by the required amount of energy by any one of the following methods, out of which the first one is going to be something called as thermionic emission. If you look at the name itself, you will get a hint. Therm refers to temperature. Ionic is when an electron is lost, it becomes an ion. So thermionic emission. So if you are able to make an electron get emitted with the help of thermal energy, you call it as thermionic emission. Am I clear with this? So that is when you take a metal and you heat it such that its free electrons get sufficient amount of energy and they can overcome the surface barrier, right? This can happen, and in this method of removal of electrons, we call it as thermionic emission, and the emitted electrons are given a name called as thermions or thermoelectrons. Am I clear with this? Called thermions or thermoelectrons. The next one is field emission or cold cathode emission. So this word is not much used. We generally call it as field emission. Name is suggesting again. If you are able to subject the metal to high electric fields, right? So when a metal surface is subjected to very high electric fields, generally of the order of 10 power 3 to 10 power 8 volt per meter. So what are the two units of electric fields? One is Newton per coulomb, or the second is volt per meter. So whenever you are trying to subject whenever you talk about the field which is used to do some work, you generally use volt per meter because work is much closer to volt, right? So if this order of field is subjected, then what you can say is electrons will get emitted, and this is known as field or cathode emission. And this method of electron emission is actually dangerous and it is less efficient also, because when you're subjected to the field, even we have some risk that is possible. Okay. So, for the electrons released from the metal surface, the electrons may also be supplied with required amount of energy. I told by any one of the methods that is over. So the third kind of emission that we can discuss is photoelectric emission. This is all about, this is the topic that we are going to discuss throughout this chapter. So I repeat it. So the third kind of emission that is possible for you to remove the electron from the metal surface is photoelectric emission. And as the name suggests, photo is from the name photons. Electric is from charge. So it is a process in which electrons are emitted from the metal surface when electromagnetic radiations. Here, when I talk about electromagnetic radiation, I'm trying to talk about light. Right? So electromagnetic radiations of sufficiently high frequency are incident on it. Here, if you see in the previous two cases, we use the word high value of field, or we used higher temperature. Here we are using the word high frequency because electromagnetic radiations are spoken only in terms of frequency. So you can either say sufficiently high frequency or sufficiently low wavelength. So have this in your mind, because we'll be doing problems based on high frequency or lower wavelength. They both mean the same. Am I clear? And through this process, whatever electrons get emitted are called as photoelectrons. This is another important word that you need to have in your list. Okay. They are called as photoelectrons, but what happens is their rate of emission is generally very low. Okay. And the last kind of emission is called as secondary emission. So it's called secondary because to knock out an electron, you will take the help of another electron. Okay. So when you have a fast moving electron that is struck on a metal surface, then what will happen is the electron which is bound to the atom will come out. Right? So how is this happening? Through the process of collision. So the fast moving electron will transfer the sufficient amount of energy to the electron in the atom, and the free electron gets emitted out. So by doing this, what are you going to achieve? The energy of the fast electron becomes more than the work function of the metal, and they get ejected from the metal surface. That's the logic, right? And the name given to the emitted electrons in this kind of a process are called as secondary electrons, and the method of removal is called as secondary emission. But as we discussed in the beginning, throughout this chapter or concept, our discussion is going to get restricted to photoelectric emission. Okay. So before you understand photoelectric emission, there are certain terms that you need to have in your mind. If you recollect, the first one is free electrons in metals. Second one is work function of a metal. Third one is what is electron volt and what is the relation between electron volt in terms of Joule. And the fourth one is what exactly is photoelectric emission, and the fifth one is photoelectrons. Right? So with these 5 terms, we can actually get started with the main context of this.
Sir,
Tell me.
sir, for secondary emission, the photoelectron should strike a metal, right?
For secondary emission, that is the fourth kind of emission now. Secondary emission has nothing to do with photoelectric emission. Secondary emission is, so there are 4 types of emission that I discussed. What are they? Thermionic, field, photoelectric, and the fourth one is secondary. For secondary emission, you take the help of another fast moving electron and you strike it on a metal surface.
Okay, sir.
Am I clear?
Yes.
Yes. So now comes the main context, you can start writing this. So first effect which we are going to talk about is photoelectric effect. So when we take a light of suitable frequency, right, when it illuminates a metal surface, then we can say some electrons are emitted from the metal surface, and this kind of an effect is called as photoelectric effect. Right. We have this word frequency in your mind. When a light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface, and this phenomenon is called as photoelectric effect. Is it clear? So, before we discuss about this photoelectric effect and the mathematical equations involved in it, first we will discuss about the concept of Hertz observations. Okay. So Hertz is the name of a scientist. So if you see, in the year 1887, the concept of photoelectric effect was discovered. But at that point, they didn't have an explanation of why this is happening. So what happened is, Hertz was performing some other experiment. Okay, I'll just put the outer concept simple. So he was trying to demonstrate the existence of what electromagnetic waves. Right? When this was tried, then Hertz found that high voltage sparks. When you have a high voltage spark that is passed across the metal electrodes of the detector loop, right? And actually, what happened is, see, this part is there. No, when the cathode was illuminated by ultraviolet light from a lamp called as arc lamp, between a curved shape. Okay, from that arc lamp, when the ultraviolet light was made to fall on the cathode, he started observing this high voltage sparks. Okay, that's what happened. But at that point, the explanation was not given. But what was he trying to do? Actually, he was trying to prove the existence of electromagnetic waves. So, what did these ultraviolet light? Ultraviolet lights is basically electromagnetic radiation, right? So, the ultraviolet light that was falling on the metal surface caused the emission of negatively charged particles, which now we call them as electrons. Okay, and these negatively charged particles were released into the surrounding, and these negatively charged particles are the ones which were responsible for these high voltage spark, which happened at that point. Right. So later came two other scientists, Halvorch and Leonard. So they tried to take up this concept of why this is happening and started doing the research. Now, during the years 1886 to 1982, Halvorch and Leonard investigated the phenomenon of photoelectric emission in detail. So what they did is they set up an experimental I would say there was an experimental setup that was done, right? So what was done is basically you logically think, if this phenomenon is given to you, what are all the required things for it? So you observe one thing, you have a metal surface, and on that metal surface, what is falling? If light is falling, you observe some sparks. And why did that spark come? Because of the emission of electrons. So if you want to observe that phenomenon, what you need? You need a metal plate. For that, they chose a zinc plate. Okay, so Halvorch connected a zinc plate to an electroscope. You know what is an electroscope, right? So what does it do? So electroscope will detect the presence of charge, right? It will have a gold leaf and it will diverge or converge depending on whether the charge is present or not. So what did he do then? Because that high voltage spark was observed with the help of ultraviolet light, they took the same light, right? He allowed ultraviolet light to fall on a zinc plate, and first thing that was observed is he observed that the zinc plate became, three scenarios were explained. The zinc plate became uncharged if the zinc plate initially, when it was connected itself, was negatively charged. So when he kept the zinc plate, had it been negatively charged, when this light was falling on it, it became neutral. Okay. and it became positively charged if it was initially neutral. Initially, when it is neutral, when this light fell, it became positively charged. What is the meaning of it? Electrons are lost. And it became more positively charged. The zinc plate was initially positively charged. So, in all the three contexts, what is indirectly told us? Electrons are lost or electrons are emitted. Right? Now, so from these observations, he concluded that some negatively charged particles were emitted by the zinc plate when it was exposed to the ultraviolet light. Okay. And one more point that was observed is as soon as the ultraviolet radiations were stopped, it was observed that the current also stopped. Well, what do you mean by current here? The charge. So from these observations, it was concluded that some negatively charged particles were emitted by the zinc plate when exposed to the ultraviolet light. Okay. Actually, there should have been a diagram. The kind- diagram. Just show you the diagram. That will stop. I'll explain the same process. So this is how the setup was done. The zinc plate was connected to the electroscope, and when this ultraviolet light was falling on it, these three phenomena were observed. You have to understand. This is what happened. So about the concept, I'll explain it tomorrow. After this, we'll be going to the Einstein's explanation. Any other doubt? Actually, there's a simple chapter only. I'm trying to explain more in detail. Self-study chapter in class. Want me to leave? I'll leave it. Because I have not yet started the main concepts. There are some graphs. You have to understand these basics. You'll see that tomorrow. Guys, the remaining part we'll discuss.
Okay, sir.
Thank you, sir.